Hi, everybody. This lecture is all about mathematical preliminaries, and it's a bit tough to get this lecture right because there's a wide range of experiences for the audience. So some students have a lot of experience and some don't have much at all. So we're going to introduce scalars and matrices today. And for some of you, it's going to be old news and review, and you can kind of zip through it really fast. But for others of you, it's some of the bits are new and a bit unfamiliar, and you might need to watch it a little bit more slowly. And so I'll try to strike the right balance so that the lecture is somehow useful for both of you. And you can tune the video, of course, so that you get the best out of it. Okay, then, without further ado, let's just get started. So this subject is often called linear algebra. That's the name I knew it as a student. I think you might sometimes know it also just as linear mathematics. That might be sometimes what it's called. But it goes by various different names, as is a kind of a theme for this module. We're going to encounter that over and over again, where there's disagreement about what things should be called. And our sort of goal for this topic is to introduce various data analysis tools. Okay, so we're going to introduce tools, and those tools are the following. The first is scalars. That's something everyone should be familiar with, though they might not know the name. The second is matrices. And the third is vectors. I expect that today we'll get through the first two, and vectors will have to start in our next lecture, which will be on Monday. I should point out, by the way, I'm using the video capture from the webcam as well as the iPad screen capture because I think everyone kind of agrees that it's useful to see a human being when you're watching these lectures. I don't know why exactly, but there's some kind of human connection that gets established from that. In the past, I've had real troubles with the audio synchronizing incorrectly to the webcam component. I think that might be cured after several generations of updates of our video capture software over the last few months. But if it's not, we'll switch to just capturing the iPad screen, which works fine by itself. It has less of a human connection, but it'll be a good second choice for how to go about things. Okay, so the first thing we're going to start out with is scalars. And scalars, a scalar number is a real number. So these are real numbers. Right, and so these are numbers you should be super familiar with. You just may not know them by that name. So a scalar, for example, is the constant a, which is, say, equal to 4.1. Or some more exotic constant like the constant b, which is minus the square root of pi times 10 to the minus 34. So these are scalars, all right? They're just real numbers. Decimal numbers if you want, but single real numbers. And you can keep on going. Lots of different things about scalars. And these are the things that you first get introduced to as a child in learning arithmetic and mathematics. And we have a variety of sort of associated concepts that you get taught right away. Associated concepts. That are straightforward things that you learn, again, in your first years of schooling. So there's addition. So for example, you could invent a scalar c that's equal to a plus b. Right, and that's something you guys know about since youth. There's multiplication. Right, and you express it like this, say like the scalar d is equal to a times b. or sometimes you might write this with a little dot in the middle. People do that, or with an X for times. There's inverting or inverse. And that works like this. You say A inverse times A is equal to A times A inverse, and that's equal to 1, right? Where A to the minus 1 is 1 divided by A. You don't have to really introduce division if you've introduced inverse and multiplication, but you could if you want. And then the last thing I'll comment on is that you have some notion of like the magnitude or the size. Right, and you write that as these vertical bars around A. You read it sometimes as the absolute value of A or the magnitude of A. And it's just the number A itself if A were positive or non-negative. And it's minus A if A were negative. Right, and so that gives you some notion of like the size of this scalar. Right, and so that's all relatively basic concepts that you would have learned as a child at various different stages. And we want to reproduce those kinds of concepts for more interesting mathematical objects. So we'll do that now. We'll start off with matrices, see how far we can get. So matrices, which is the plural of matrix. So these guys are a grid of scalars. You can actually have matrices filled up with other things like complex numbers and even other more elaborate objects, but let's just stick with this definition. It's simple enough for us. And we'll say, it will just give you an example. So, and I'm going to use, we will usually restrict to capital letters for matrices. Not always, but usually. And so let's say you have this matrix A. And it's a grid of numbers. And so let's make this grid the following. So we'll say it has A1, 1 over here, A1, 2, and A1, 3, and then A2, 1, A2, 2, A2, 3. Right, so this is a 3 by 2 grid. Sorry, that's not the right way you say it. You read it, the number of rows by the number of columns. So this is a 2 by 3 grid. All right, so here we say, well, there's different ways to express this too. So sometimes you just write it like this. You say this is square brackets around little a, I, j, like that. Sometimes you write it like that. And sometimes you say that little a, I, j is equal to, this is just some notational stuff that you'll run into, ijth element of the matrix A. So these are the elements of the matrix A. Right? And so as you can see, these things, so here I is the row and J is the column. That's the standard notation there. So A2, 3 is the number that's in row 2, column 3, right? And we say that there's a dimensionality to the matrix. So A has dimension two by 3. That's the thing I misspoke earlier. Or sometimes you just say in short A is 2 by 3. That's the short version of saying that. Right? Okay, so that's what a matrix is. It's a grid of numbers. Obviously, the dimensionality doesn't have to be 2 by 3, but we will take it always to be a two-dimensional grid, so that it doesn't have like a depth or anything like that. And so that's what a matrix is, or those are what matrices are. And now what we want to do is introduce kind of various concepts associated with matrices. How do you add them together? How do you multiply them? What does it mean to have an inverse? Things like that. Right, so we're going to go first with matrix addition. Right, and matrix addition works like this. So we'll say, let's say you have two matrices, A and B. These guys are both matrices. With the same dimensions. That's kind of important. It's pretty crucial, actually. Without this, the definition doesn't work. Right, so it's only going to be possible to add matrices if they have the same dimensions. Then we say the following. So we say the matrix A plus B, its ij element is equal to the ij element of matrix A plus the ij element of the matrix B. All right? So that's how matrix addition works. And we can do a simple example. Okay, so let's just do 1, 2, 3, 4. Oh, and incidentally, there's no meaning to me switching between square brackets and rounded brackets here. I just go back and forth. Let's try to say we tried to add that to 0, 1, 1, minus 2. Right, and so what do we get? So the output is also going to be a 2 by 2 matrix. And the first element, so we're going to start to build it here. The first element is this guy plus this guy. Right, so that's 1. And the second element is this guy plus this guy. So that's 3. And so on. And so we got 4 and 2. And you should see from that why you need the matrices to be the same size. So if the second matrix there had a third column, what would we do with it? How it doesn't, the rules don't explain what to do. You could of course invent a rule that would allow that. But the rule that we're inventing and that we're going with does not allow that. Okay, so the next thing we want to introduce is matrix multiplication. Okay, and so we'll introduce two matrices, okay? We'll say if A is a matrix, and let's say it has dimensions m by n. So m rows and n columns. And then B is another matrix, and it has dimensions n by q. Right? Then what is the meaning of the product of matrices A times B? And here's what it is. So A times B, a new matrix, row I, column j of that matrix is the following. It's equal to a sum over the index k, and k ranges from 1 to n, where n is the common value for those two things. It's the number of columns in A or the number of rows in B times A row I column k and B row k column j. Right, so that's how you write matrix multiplication. It's good to, so there's a lot to say about matrix multiplication, and I think the first thing I want to do is actually do an example, and then we'll talk about some properties that are pretty important. So let's try to do an example. So let's try to multiply these two matrices by each other, right? And then we'll talk about how that goes. So I'm going to copy them. Okay, and I'm going to sort of rearrange so that it looks like multiplication. And I'm going to discuss to you how I do this. So there's sort of two ways to go about this. One is you could just stare at the sum and work out the sum by hand. That's certainly how it's done on a computer. And you will be doing these things on a computer more so than by hand. However, whenever possible with something you have a computer doing for you, it's important to be able to do it yourself as well, at least in some form, so that you can check that you've done it right. Not to say that computers will be making mistakes, but you may have told the computer to do something that is not what you think you told it to do. And sometimes the best way to check that is to manually walk through some of the calculations and make sure things are what you expect. And so it's crucial to be able to actually do that. You don't want to be flying blind and just trusting everything a computer tells you, because they have this painful property of only telling you kind of the truth. And the truth isn't always what you had intended. So, yeah. Okay, so let's go ahead and do this matrix multiplication. And I'm going to start by sort of looking at this line up here, but then I'm going to do it kind of the way I do it in my head. So I want to look, so the first element of A times B, so that's AI equals 1, J equals 1. So it's going to be this sum over here with 1 here and 1 here. All right, so it's going to be a sum over K of row 1 of A going across the row and column 1 of B going down the column. And so what that looks like is, right, so going down the row 1 of A, so we got 1 times, and then here we have B 1 1, so that's 0, plus, so the second term, A row 1 column 2, so that's 2, B row 2 column 1, 1. Right, so that's the first element. Right, and so what I do when I see this is I kind of imagine taking this column, I sort of have this picture in my head, moving it over here and making it horizontal, and then multiplying that by that and adding it to the multiplication of that by that. So you have to have kind of like this animation in your head of this thing going over here. Then you end up with 0 and 1. So 0 and 1. And you multiply that by that and add it to the multiplication of that by that. So that's what I have that kind of in my head. I actually literally kind of imagine this thing moving over here and going sideways and then merging with this first row. You might want to set up some kind of animation like that in your head, because it gets confusing to stare at this sum all the time and try to do that if you're going to be doing these by hand. Now usually instead actually you end up just not doing these by hand, and you are happy to look at the sums because this is kind of all you really care about, and you're not really doing the details by hand, and so that's fine too. Okay, and so for the next one, we move this same, I'm going to do it by my head method now. I take this column again, move it here, make it sideways, but now I merge it with the second row here. All right, and so what I get is 3 times 0 plus 4 times 1, right? Now for the next element over here, I get 1 times 1 plus 2 times minus 2. And then the last element, I get 1 times 3 plus 4 times minus 2. Like that. right? And then you do all those additions in here. So let's see, this first element is 0 plus 2, so that's 2. The next one is 1 minus 4, so that's minus 3. The next one down here in the lower left is 0 plus 4, so that's a 4. And then we've got 3 minus 8, so that's minus 5. And that's the result, okay? Now, again, you won't be doing these by hand very often, and this is a perfect kind of activity for a computer to do, because there's lots of room to do it by hand when doing it by hand to make mistakes. You know, everyone is bad with making simple arithmetic mistakes. So you would like to avoid that if you can, but it's crucial actually that you know how to do it at least. Okay, so that's matrix multiplication. Now let's say a little bit, there's some important properties to understand here. Some rules, all right, so comments or notes. Note the following. These are some important things about matrix multiplication. So first of all, what are the dimensions of the matrix A times B? And now to do that, let's go back up here and what we see here. So A has dimensions m by n, B has dimensions n by q, and then they're built like this, right? And so what values can I and j take on here, right? So I points to the row index of A. And how many rows are there in A? M. And j points to the column index of j. And how many columns are there of j? There's q. So this thing has dimensions m by q. Okay? So that's important to understand. The next thing that's important to understand is that the product B times A, so putting them in the opposite order, in general does not equal A times B. That's very different from multiplication of scalars. It's a new property. And in fact, B times A may not even exist. Right? And so how come that is true? Well, let's look here and see. In order for the matrix multiplication to work, right, it has to be the case that if I pick up this thing and move it over here and make it sideways, that it actually fits, that I get the same, you know, so like it's got to be the case that the number of rows here matches the number of columns here. In other words, this number has to be the same as that number. And so if you were to do the operation, do the multiplication in the opposite order, right? So if we were to look at, so let's put it on the side here. Well, let's look at it down here. If we were to try to do B times A, that'd be a multiplication of a matrix with dimensions n by q times a matrix with dimensions m by n. But m and q are not equal, and so that's just not going to work, right? For this happens when m is not equal to q, right? It won't exist if m is not equal to q. Now in the example we did, you could multiply the two matrices in a different order, and you'll almost surely get a different result. I encourage you to try it. And the reason you can do that is that those two matrices are what we call square. The number of rows is equal to the number of columns. And so they were matched up nicely to do matrix multiplication in one direction, and they would still be matched up nicely to go the other way because they were square. Okay, just a couple of simple notes also. The following is true. If you have matrix A and you're multiplying it by a matrix B plus a matrix C, this is equal to, you can distribute this, A times B plus A times C. Right, so that's one thing to know. Also, now I'm not quite sure what's the best way to say this. Let's say you make a matrix C and it's equal to, let's say, what constant do I want to use here? Let's say I say a constant alpha, so that's a scalar, times the matrix A, right? Then what that is is a matrix where row I, column j of C is just equal to the scalar alpha times row I, column j of A. So in other words, the scalar multiplies every single element of the matrix A. All right, so that's all I want to say about matrix multiplication for now. And we'll move on to matrix inverse. Sorry about that. My screen goes out of whack every now and again. Matrix inverse. All right, and we're going to use a notation that matches what we saw for scalars. All right, so we're going to say that a to the minus 1 power, that means the inverse of a, times a, is equal to a times the inverse of a, and that's equal to, I'll call this capital I, where capital I is called the identity matrix. Now this looks like the equation we saw for scalars, and in that case the right hand side was the number 1, and the identity matrix is very much like the number 1 in matrix form, in that anything it multiplies, so long as the multiplication is allowed, it just gives back the same thing that it multiplied. So it's like the number 1, and I looks like this, so I, row I, column j, is equal to 1 if I is equal to j along the so-called on diagonal. On the diagonal of the matrix, and it's 0 otherwise. So off the diagonal. So in other words, the matrix I looks like this. 1, 0, 0, and there might be more of those. And then how do you write this? You know, it looks like that. So it's got 1s along the diagonal, right? And then the last row would be 0, 0, 0, 1. Just let me fix this up, make this a little bit better. Right? So the only places that are not 0 are on what we call the diagonal, and that's the identity matrix. And of course it has to have the right dimensions to be, so there's identity matrices of different dimensions. Notice that it's square, and so there's like the 1 by 1 identity matrix, which is the number 1. There's the 2 by 2 one, which is so on. Okay, and so we'll make a little comment here. Note, this requires that A and its inverse have the same dimensions. And it requires that because of the fact that you've got them in the opposite order here. The only way that you could flip the order of the matrices and have them still be, have the multiplication of them still make sense is if they were, is if they had the same dimensions and if they were in fact square. So we'll write that down here as well. And they are square. Right, so what I mean by that is A and A inverse, oops, are n by n for some n. Okay. It's important to understand that there may not always be, even if A is square, it may be the case that there is no inverse of A. And we'll talk about that in a second. That's also true for scalars, right? So under what conditions is there no inverse for a scalar? Well, there's no inverse for the scalar 0, right? There's nothing you can multiply 0 by to get 1. And so we'll see something about that here. So we're going to introduce our last concept for today, I think. Oh no, we have one more after that. The matrix determinant. Right, and so the matrix determinant is the closest thing to like the size of a scalar for a matrix. So it only works for square matrices. So if A is square, so again, that means it's n by n, where n is some integer, then this symbol represents the determinant of A. Sometimes people use this symbol, but actually, if you really want to be kind of as unambiguous as possible, you might write it like this, DET A, where det, or DET, stands for, is short for determinant, right? This thing is called, it's called the determinant hope I spelled that right, of the matrix A. My spelling is super atrocious, so don't follow my spellings for anything. So that's called the determinant of A, and some things to understand about the determinant. So first of all, it's a scalar. And in that sense, it's useful to think of it as some sort of a size associated with A, because it could be, 12 or 11 or a million. It might give you, I don't know, for some reason that gives me a sense of size, a scalar number. Also, however, if the determinant of A is 0, then the inverse of A does not exist. And that's similar to scalars in the sense that if the absolute value of a scalar is 0, in other words, if the scalar is 0, the inverse of the scalar doesn't exist. That's a really special scenario for scalar numbers because there's only one number called 0. But it's not special for matrices. There are lots of matrices that have determinant 0 and that have no inverse. In fact, it's frightening how easy it is to construct such a thing. So let's actually do a determinant. So now determinants, there's not a really simple way, I think, to express out how does one calculate a determinant. I think it can be done, but it's a little bit messy and heavy-handed. So instead, I'm just going to do 2 different examples, and hopefully it will become clear how it works. All right, so let's do some examples. Let's make a matrix A, B, C, D, and we'll take its determinant. Okay, so it's a 2 by 2 matrix, and here is how it works. All right, what you want to do is you multiply A times D, and then you subtract B times C from that. And in your mind, you should be making that little shape there, right? So this is A times D minus B times C. So that's how you do the determinant of a 2 by 2 matrix. And for a 3 by 3 matrix, which is the last word where I'll stop with these, it looks like this. So let's say A, B, C, D, E, F, G, H, I. This determinant, you're going to build it up as a bunch of 2 by 2 determinants. So the first thing you do, so we're going to go along the top row, right? So we're going to go along this top row. We take the letter A, and then we multiply it by the determinant of the things that are not in its row or column. Right, so let me write that out so maybe it's more clear. A times the determinant of E, F, H, I. right? So those are this guy, this box here. And they're all the elements that are not in the row that A is in and not in the column that A is in. Right? And then the next thing you do is you subtract, so we go alternating, plus, minus, plus, minus, plus, minus every other term. You subtract B times the determinant of all the elements that are not in either its row or column. So I'll write them out here. So that's DF. G, I, like that. And then the last term is an add of C times DE, the determinant of DE, G, H, like that. So that's how you do it for a 3x3 matrix. And for a 4x4 matrix, you kind of build it up in a similar way, where you would get a line like this, where you'd have 4 different things with an alternating sign here, but the coefficients that they'd be multiplying against would not be 2x2 determinants, but they'd be 3x3, and so on. And you can build up from there like that. So you should know how to do determinants, and that's kind of how they go. Okay, so the last thing I want to introduce today is called the matrix transpose. This is not something that exists for scalars. Oops. All right, and the notation we use for it is a superscript of the capital letter T. So we say A with a capital T superscript is the transpose of the matrix A, right? And here are what its elements look like. So the transpose of the matrix A, row I, column J of it, is equal to row J, column I of the matrix A. So in other words, the rows and the columns switch places for a transpose. And so let's do an example. 1, 2, 3, 4, 5, 6. All right, so that's a 2x3 matrix. Let's take its transpose. And it looks like this. 1, 4. So column 1 becomes row 1. Column 2 becomes row 2. And column 3 becomes row 3. Like that. And if you, of course, transpose that again, you get back to the same thing. You should be able to see that. Right, so column 1 becomes row 1, and column 2 becomes row 2. Like that. Right, so you get back to so transposing a matrix twice gives you back the original matrix. Just a couple of comments about how transposes work, so some properties. So note. For A m by n, so if the matrix A has m rows and n columns, then A transpose has n columns and m. Did I get this right? Yeah. N. I might have spoken it wrong, but the dimensions swap. How's that? Right? And so as a result, right? So if A and A transpose are like this, notice the number of columns of A is the same as the number of rows of A transpose, and the number of columns of A transpose is the same as the number of rows as of matrix A. So therefore, A times A transpose and A transpose times A always exist. Oops, exist. So it's always okay to multiply A by its transpose or a transpose by the original matrix. The dimensionality is okay. And one last sort of weird cutesy set of properties about these guys is to say, so this is like a note here, and here's the next note, which is that the transpose of a sum is equal to the sum of the transposes. And this one is really fun. The transpose of a product, oops, I don't know if it's fun, it's a little bit surprising, is the product of the transposes but in the opposite order. Like that. You can check that. I recommend you try that out and see if you agree. Give it a try. Put in my examples. Or make your own examples and see if you can do that.
Okay, so that was our introduction mostly to matrices. And I hope that I struck the right balance to make this lecture useful for kind of a broad range of people, and that you got some use out of it. Next lecture, we'll discuss vectors and some other mathematical preliminaries for multivariate analysis. Until then,